Thanks for the warm introduction. So we're going to be talking about smart contracts. While initially I was not really big on blockchain and everything, I didn't really care. But living in Dubai, everybody's talking about it all over. So I was like, if at least I'm going to be criticizing it, I may as well be educated about it. So that's how I started to look into it to know what were the leading blockchain platforms. So I started to look at it back in February. And ended up writing a decompiler for Ethereum bytecode, which was pretty stupid of me. I wish if I'd bought some coins instead of writing a decompiler. At least I would have made money out of it. But at least I got an excuse to come back to ShackAcon. So this is my Twitter handle, Suiche. So I'm the founder of a company called Deccompiler Technologies. We just started around 1 year ago. And like Jason was saying, I'm also running a conference called Upcode in Dubai. We just like focus on like technical content. And yeah, I'm mainly known for, so you can see I've been lazy, huh? Because some of the lines are for my DEF CON thing. I'm mainly known for like Windows stuff. So I wrote an application deployment software called Cloud Volumes, and wrote a bunch of memory forensic utilities. Yeah, and my new claim to fame is I've been called a fun guy by the shadow brokers. So just so you know, even though it's blockchain related, we won't be talking about like the most of the blockchain stuff that people are talking about, like the Merkle trees, proof of work, or all those things. Mainly, we're going to be focusing on the Ethereum virtual machine. We're going to talk about their compiler called Solidity, and we're going to focus on smart contracts. So that's the agenda. So what happens with Ethereum is that basically introduce that concept of dynamic application. So if you look at standard blockchain stuff, it was just like data being stored on blockchain. But since Ethereum, so when they came up with that concept of dynamic application, so like, oh, we can store basically like software on top of blockchain, and that's basically what they call a smart contract. Usually that would be like a very small piece of code that would be compilable by a compiler called Solidity. The syntax of smart contracts is very similar to JavaScript. And when I came up with the idea of doing the decompiler, well, I was like, well, if the compiler is called Solidity, I'm just going to call it porosity. So if you have done some physics, you would know that that's basically the opposite of solidity. Just to give like a short introduction about like Ethereum. So basically what I was explaining before is so with dynamic application, you can have like basically you have so bytecodes that you store on blockchains, and that is going to be interpreted by what they call the Ethereum virtual machine. So it's not as advanced as what most of virtual machines we know. Even if you would take like some old Game Boy emulators, they would be like more like powerful to a certain degree, except when it comes down to crypto functions. So what we will see also is like with that VMs, also like hardcode, virtual crypto like functions. So each blockchain will basically be like an account. So blockchain account and contract are basically like interchangeable words. A smart code is made of bytecode, which is what we're gonna like look at during this presentation. And one of the specificity is that it operates two 56-bit register. They're not exactly like the register we would know with traditional architecture like x86. Instead, it's using like a virtual stack where it keeps pushing like those registers in the stack. And for each addresses, which correspond to an account or contract those are encoded on 160 to 160 bits. So just to give you an idea of what's a smart contract, so here on the left, that's basically what Solidity takes as an input. As you can see, it's very similar to JavaScript. The syntax is very simple. So that's basically a smart contract designing a coin. So as you can see, it's like pretty straightforward. In that case, it's like 20 line of code. In the case of the DAO smart contract that got robbed last year, it was like larger. It was like maybe like 200 line of code, but they stay like relatively small because the idea is since you have like bytecode on the blockchain, well, you want to keep it as small as possible, right? But it also means if a contract has a vulnerability, you cannot really patch it, which is one of the main problem like so far. And that's what resulted in a fork when the robbery happened last year. So just to go like shortly through the attribute. So here at the beginning, you see the types. We have like address, which is like a single variable. Then we have an array called mapping that basically translate addresses into a value, which in that case would correspond to the balance. And then here we have 3 different functions, coin, mint, and send. So if you look at send, it's pretty straightforward, just basically like an addition and a subtraction. So nothing really complicated per se from there. And once you compile it, so on the right, so in the top part, you would see like the runtime part, which is basically like the translated bytecode, which is, I don't know if you have done like reverse engineering, but it's very similar to like disassembling code once you like look at it. But in addition of that, the second part with the ABI for the interface, that would pretty much correspond to like the symbols of that smart contract, and at the end, the hashes are basically like the identifier to each of those functions. So, and we can see like our functions at the bottom. So when it comes down to memory management, which is like a big part of every virtual machine. So here we're gonna distinguish 3 different types of memory. So the first one, like I was mentioning before, is what we're gonna call the stack, but think of it as a virtual stack because it's kind of like replacing registers, and we're gonna see after when we're gonna see all the functions are being called or it's being used. One of the specificity of that stack is basically it's limited to 1024 frames, so you cannot go above that, which can also be a problem when one contract is calling another contract, and then you have like your stack chain just growing too quick. And the second one is like the storage. That's basically like the key value storage mapping. If we go back in that contract, that would be like the balance at the beginning. It can be enumerated internally, and when we're gonna look at the Ethereum assembly code, it's gonna be easily recognized through the so storage store and storage load instructions. And the third one is basically like the well, what would be like normally like the stack or like the heap. It's a volatile memory. Basically, it works with like everything is working with 2 56-bit values, and same thing here. We can recognize it through the mstore and mload instructions. So, regardless if you're writing a decompiler or doing some static analysis or dynamic analysis, one of the first things you want to understand with any binary code or assembly code is how do you identify basic blocks. So here, because like the VM is very very straightforward. There is a very quick trick to recognize basic blocks. Is basically there is an instruction called jump dest, so for the to mark the destination of jumps. So in most of cases, not all of those cases, each basic block is going to start with this instruction, and then so we have like jump instructions. So there is multiple, just like with x86 assembly, we have conditional jumps, straightforward jumps, but unlike other like I would say like assembly languages, while the way we know the destination is by reading that virtual stack I was mentioning before. And so every time we would see a jump, usually we'll see like a push instruction before. Most of the times, not always, there are like some cases where the virtual stack will be like swapped. We would see like deduplication on the stack itself, or even like some pop to get the destination address. So there is no concept yet of like malicious or obfuscated like EVM code, but that's something that could be done very easily, and that could confuse a lot of the confuse like the Ethereum network. Because now if you look at the actual like on the Ethereum website, like the number of contracts, there is only like 1,000 verified contracts out of like 1 million account. And to be a verified account, you need to provide source code. So that's what they call like a verified account. So how do we know if that's the same source code, or what happened to like all the other contracts that are not providing source code? Well, so far, so until now, there is no like solution to it. So like the EVM, like I was saying before, it's a very like simple VM, plus it also integrates a bunch of cryptographic functions, like SHA-free. We're going to see a lot of the regular arithmetic instructions, comparison, and all those regular instructions. The environmental and block information is basically the instruction specific to read data from, like on Windows, we have like the processor environment block. So with EVM, they would have something similar, except for the process, it will be giving you the address of the sender that sent the money to like the actual contract or the caller. And then like the stack and memory architectures that we just saw, and you can also like log operations. So in the case of an addition, for instance, so that's where you see it's kind of like assembly code, but it can be translated into an intermediate layer quite easily. So here for an addition, so we would push like the 2 arguments to the stack, like with a standard call procedure, and add, which is an actual opcode, will behave like a function. So in that case, it takes 2 parameters. So that's the EVM pseudocode right there. So obviously, once that instruction is going to be executed in the first entry of the stack, we're going to have the result, which is going to be free. And then we have a second type of instruction call. So the first one comes down to instructions themselves. But there is also an instruction called call, which allows to call external contracts or external accounts. So here we see like the actual format for the call. So the first parameter will be like the gas limit. So one of the specificity of the EVM is that basically you allocate, just like with instruction cycle in a regular on a regular machine, you can put a limit to it, so you are sure it won't exhaust too much computer power. And so the second parameter is like the most interesting one because it basically contains the address we're going to use to call that contract. So that's the address of the contract itself. And with the exception of 4 contracts that are hard-coded inside the EVM, which is basically like the one for the elliptic curve public key recovery, SHA-2, and because SHA-3 is an actual instruction on its own, RIPE MD 160, and the identity function. So the fact, even like from the instruction point of view, the fact it's so easy to retrieve those instructions, if someone would just happen to recompile Ethereum, it would be like very easy for them to write like an Ethereum rootkit or something as such. So they would just like intercept all the calls if they would want to track more information out of it, or even change like destination addresses. Or even actually, like even patching the process in memory would be quite feasible. You would just have to hook like that specific instruction directly. Then, so previously we talked about the environmental information block, which you can access using the opcode like call data load, which is basically like the equivalent of a get command line call. So you would read that whole block. So the first 4 bytes are basically the hash of the function we want to call internally inside the contract, and then it's followed by the arguments. And the way those arguments are going to be ordered is going to depend of the actual function definition. So that's why if we go back to the initial screenshot here, in the middle, that's where like the ABI is very important because it contains like the symbol or the definition of your actual functions. But by reversing a contract, assuming you don't have the ABI, you can also extract those hashes. So here is like a basic function. So just doing an addition. Here we have like the intermediary Ethereum code. So we read like the first argument. So we're gonna see like a call data load, then the second argument, and we just add each of them. So, like I mentioned before, so when it comes down to type discovery, there is 2 ways to discover like types. The first one would be using like the symbols, like the ABI symbols I was mentioning before, or the second one would be to actually look at how those like variables or arguments are being masked. So in the case of addresses, for instance, like I was saying before, like the specificities, even though like the EVM is working with 256-bit registers, addresses themselves are encoded on only 160 bits. So usually you would see an AND operation with that following mask. So you would see it either statically or dynamically. Like in the case below, that mask is being computed dynamically. But those are like quite standard and they are like pre-compiled already. And from that you can, so in our Deccompiler porosity, if we recognize that sequence of code, we would just like mark the attribute of that specific register in the virtual stack as an address based on those parameters, which helps later on when it comes down to going from an intermediate view of the EVM code into like Solidity-like source code. So now, regarding the actual bytecode, so just to go back initially. So now, so here, if you look at the top, like the command I'm using to call Solidity, I'm using the argument dash dash bind runtime. So the only part I have here is only like the runtime part. But if you only use like dash dash bin, it's going to also include the preloader, which is going to be used to copy the actual smart contract in memory. So I'm going to describe that preloader, which is specific to most of the contract. So the preloader, like the name says, can be found at the beginning of each contract and is in charge of bootstrapping the contract. So it's gonna, it contains like the actual size of the runtime code and is gonna copy it in memory. And then the runtime code of the contract starts at the instruction address like 0, offset 0. And that's where we have all the logical routine with all the function we define in our contract, and also like the definitions for like the actual storage variables that we would see here on the top. So like I was saying, so basically it contains like the actual logic flow of the contract. So the way it works is once you enter in the preloader, you're gonna have like a big like switch statement like a dispatch table that would redirect to each of the function we defined. So here, what we see now is basically the preloader. The most interesting like instruction here is basically like code copy, which is going to be in charge of reading the actual runtime code and copy it in memory to be actually like executed by the Ethereum virtual machine. Most of the instructions we see before are quite like standard instructions. Here we would see like the address of the actual contract where it's stored, and like the size of the actual contract. So once it's copied in memory, so then comes like the actual dispatcher, and so here it's an example of a very simple contract with two functions that we can see here in yellow and pink. So like I was explaining before, due to the architecture of the actual VM, most, except like push instructions, most of opcodes are just like single, don't take any parameters, and would read from the stack directly, which requires, in most of cases, to dynamically like emulate most of the instructions, especially when there is a lot of operations regarding the virtual stack. So here, if we look in orange, like I was explaining before, it's going to read the environmental information block, and it will start by reading the first 4 bytes. So here, the optimization is basically, it's going to read the whole 256 bits inside the block, and then it's going to use a divide instruction to basically extract those 4 bytes. And then it's going to compare those 4 bytes before like switching to the actual function. And on the right part, we see like the actual 2 functions for the multiplications. So in the middle, basically, there is a common common basic block. So, which is quite interesting because they managed to have like some sort of like code optimization, which so far works pretty well with their EVM, even though like I'm going to explain at the end of the presentation, they're going to move towards a new design for their binary run code. So, and like I was explaining before, so here, each time you see a jump, basically you see like a jump desk to ensure the integrity of the destination. The function hashes are not generated randomly. They actually follow like a specific design. So it will do like a SHA-3, so a KCAC 256 of the function name and then the type of each parameter. And from that, so in that case of double, for instance, let's say it takes only one parameter. So in the second box, we would see it would just like extract like the first 4 bytes of that hash, and that would be the actual hash that we would see in the previous screen. So here we see it's EE E9, and here in yellow we see it's basically EE E9 in backwards. So that's just like to illustrate the code optimization to extract the actual parameters. So here, assuming like you pass a 256-bit register containing like the hash 1, 2, 3, 4, 5, 6, 8. So the division would just extract it, like we saw before. And here, so that's an output generated from the tool regarding the control flow graph. So on the left is basically what comes out if you just like generate the graph statically. So in most of cases, even though like for that example that was very straightforward and very simple, you will still need to emulate it to make sure to retrieve all the parent caller for each basic block. So here, for instance, we see like the basic block at 4F is an orphan block because of stack manipulation operations that I was mentioning before. Because if you see like a jump, but before you would see like a pop or like another like stack operation which is not a push, well, you don't really know where it's going to point unless you're like actually emulating like each basic block. Which fortunately is something like we can do very easily by writing an emulator, especially since there is no concept of registers to save, and everything is basically like a virtual stack. It's pretty easy, like in our code to fork like the state of the virtual machine, because it comes down to mainly like the virtual stack, which is, you know, even though the maximum is like 1024 frames, usually it will be like around 10-ish. And when it comes down to the persistent and the volatile memory, it's like a very small buffer. So if we translate the actual dispatcher into like pseudocode, that what would come out of it, and then on the right would be like the the decompiled view of it that we would manage to extract from it. So most of memory operation using like mstore and mload will be like temporary. So that would be like the temporary buffer. So we just ignore them with the decompiler, and the actual like Suiche, like I was explaining, each case would actually be an actual function. So if we have access to the ABI definition, we can just like do like some sort of regression and extract the actual function name from that. And then we would also have like the type of the parameters. But even without the symbols, we'd get kind of like abstract names, but that would still like be understandable. So here, let's say the double function had been called. So the first 4 bytes would be the hash of the double function. Then from there, it will so that we would see like the call data load that would read the actual first parameter at the offset 4. Actually, I don't know if I can. See it here. Yeah, here that would be the offset where we would read the first argument, and then here we would see like a push 2, and then it would enter in the new basic block, which is common to the two functions. So here, it's going to be on a jump dest, but it won't do anything because there is no jump before, so that would be the equivalent of an up instruction. And yeah, and just right after that, it would just like call the the multiplier instruction. And here, in the case of the triple, so instead of pushing 2, it's going to push 3. And then here we would have an actual jump that will actually give the offset and just go there directly. And then execute the multiple instruction. So here is an example of a vulnerable contract. So like I was explaining before, so like the kind of like the nice thing about it, like of introducing like smart contract, like the concept of a smart contract is interesting from a software point of view, from an application deployment point of view. And they would be very simple, but since they're introducing that concept of a software layer, well, it makes them vulnerable to actual vulnerability, because everything which is software is going to see vulnerabilities anyway. It's like the Murphy's Law. So here, the actual vulnerability is basically in the withdraw balance function. So because here, what we see is like the equivalent of a race condition. So, well, most of JavaScript developers have never heard of race conditions. So it took them by surprise, and that's basically what resulted in DAO losing 60 million last year. But that's basically the type of vulnerability that was in Toast contract. And even conceptually, since everything is on the blockchain, well, you have access to all the applications that are on the Ethereum network. So here, basically what happens is when it's taking the balance out of the account, well, the balance is being initialized to 0 after. So before that, if there is an actual like error, what can happen is the caller, which is another contract, can have a fallback function which is executed by default. So that's what people in the Ethereum community call the reentrant vulnerability, which is basically like a race condition. So the good thing is from the Deccompiler point of view, because it's also like an emulator, basically, which helps us to retrieve all the basic block. We can track each block which is doing a memory instruction on the actual like persistent memory. So like I was saying before, while it comes down to one single instruction, which is called ssstore, and which is the one initializing the balance. So if we see like an external call to an external contract that had been made before that, we would just flag it because some untrusted call had been done right before. I can just show. Can you see my screen? So here that would be a vulnerable contract. and basically we would get that bytecode, right? And we're just gonna pass it to the actual decompiler. So on top, so is like the actual source code, and then we're just gonna pass that bytecode to the decompiler, and that's the translated code out of it. And we can see it's highlighting the vulnerability, which is like the rest condition in the withdraw balance code, which is kind of neat because it's pretty straightforward due to the like the complexity of Ethereum, which is like quite straightforward from that aspect, since it's like a VM, it's not an actual like entire machine. So that's basically what we just saw now. The decompiled code and the vulnerability, which is flagged due to the previous parameters. So far, there are like 3 main classes of bugs with Ethereum smart contracts. So that's only like the case of Ethereum. I haven't looked at other like platform like Hyperledger and everything. But by definition, if they're like putting some software tied to any like blockchain stuff, while people are gonna have to chill on saying that while we're using blockchain, so we're secure by default, because that's not the case if you just add some software layers on top of that. So the first one is so the rest conditions that I was saying that was used last year to steal 50 million. The second one is the cold stack issue. So if you use like all your stack frames, it can create like some undesired behavior, and it will not even generate an exception. And time dependency vulnerability, well, that's pretty cool. So there is that guy, Sven, who published some example where basically, since everything is on the blockchain, including the data, while you actually have, well, even in general, like, but by definition, like each block that would be replicated across like the network would also contain all those informations. So yeah, he was giving the example of a casino. So he would be able to predict like the random function, because they're not actually random. They're using like some information from the header of the actual blockchain. And recently, so one of the lead developer of Solidity compiler just launched a contest this month called the Underhanded Solidity Coding Contest, which is quite interesting. Like they're gonna publish like the results like next month. But the idea is to ask people to write vulnerable code and to put backdoors in it, but to hide them, because like we saw before, especially in the case of like that rest condition, or even like most of vulnerabilities that you would see with smart contracts, they are not as obvious as like Stack Overflow or Buffer Overflow or like those things. So the whole like idea of the contest is around like ICOs, which had been pretty hyped over the past few months, and to put some backdoors in it, because now we're gonna see a lot of people trying to do like ICOs, which is like the crypto version of IPOs. So they're gonna have to use smart contracts for that, which is gonna be like quite interesting. Like the interesting part about Ethereum per se, well, I don't know if people are still gonna be using Ethereum in 5 years, but the thing which I find quite relevant and very significant with that is basically they're the one who introduced that concept of softwares on top of blockchain. Well, if by definition, if it's a good idea, you know, like people have various opinions, right? Especially since you cannot really like patch applications as easily as regular software. But we're probably gonna see like more and more of that, and it already started because now everybody's talking, like, especially when it comes to enterprise blockchain, more and more people are talking about smart contracts. And like I was explaining before, everybody was talking about it, but every time I was asking what's a smart contract, nobody like really knew to answer me. That's how I ended up like looking at Ethereum and discovered they have an actual virtual machine. So Porosity, I'm gonna release, like, it's gonna be open source. I'm just gonna like release it at the end of the month. when it comes to like Ethereum security and like smart contract security, there is like actually a growing community that happened over the past few months. There is also like a tool which does also contract analysis called Oyente that had been released also like recently. Like I was saying, I'm personally looking forward like the coding contest results to see what type of vulnerabilities people are going to be able to demonstrate, or if new classes of bugs are going to be discovered. And we saw like some project like Quorum, which is JP Morgan fork of Ethereum, adding a privacy layer to blockchain stuff. Like I was saying, now, like you basically have a copy of the virtual machine state all over the network, right? So nothing is really private; everything is public. Which again, like if you're a software developer, you're like, why? You know, you don't really want that. So JP Morgan like added one more layer to that to be able to have private and encrypted variables inside the data. And from a lower level point of view, like I was saying, it's basically a virtual machine. So we have seen like plenty of vulnerabilities in QEMU, even in VMware, on most of hypervisors. So like there is no reason to not see something similar happening with Ethereum VM. And like the only thing that would save them is basically that the VM is quite small. It has a limited set of instructions, but you know it goes both ways. You know, like they're kind of claiming as like purely sandbox, blah blah. But we know what happens to sandbox vulnerabilities, right? But the interesting thing that I discovered like a few weeks ago is basically Ethereum is planning to replace their Ethereum virtual machine by next year with WebAssembly. So first I was like, oh, what the hell is WebAssembly? And then I was like, oh man, that's pretty nuts. So they're planning to do that by next year. But basically, like WebAssembly outside of Ethereum is allows you to run like even like C++ application in JavaScript. Like one of my engineers sent me an actual like web compiler where you give him give like C code, and he's gonna translate it into like assembly and launch it like locally. Which is pretty new. That's pretty like crazy from an attack surface point of view, because so now like you have like V8, Chakra, and SpiderMonkey actually implemented WebAssembly. So Ethereum is going to use the same engine for like WebAssembly, and it's going to replace their like virtual machine. So from the Ethereum perspective, I guess it's good because they're going to have a larger community of people working on it. But on top of that, you're going to have a more powerful like virtual machine. But then again, like like executing like C++ application in your JavaScript engine, you know, I don't really know what's going to come out of it. When it comes to the Ethereum implementation of that, so at the end, the EWASM contains all the design information regarding to it. And yeah, that's basically what they say. So if you go to that address, actually, you can see the actual compiler I was talking about, which is like a pretty cool demonstration from a software engineering point of view. But from a security point of view, it raised a lot of questions. So they're planning to do something similar for Ethereum. And so like I was saying before, if you would write a smart contract now, that would be basically like JavaScript code that you would compile with Solidity. And so for next year, once they have the actual portage of the WebAssembly for Ethereum, they're going to also give you the possibility to write contract in C. But those are like C applications you will not even be able to patch. So like unless I'm missing something, you know, I ask a bunch of people like, but that's pretty crazy. You know, it does not make any sense from a software like design point of view. And those are like some references if you want to read more about it. Any questions? Was Bitcoins? Okay, well, thanks.